Hey there, it's Dr. Jen. As promised, here is your lecture on chapter 6 and 7. Now, the good thing is that the information is pretty basic. You guys have had a lot of this before. Let's get cracking, and you will need my slides for this presentation, and you will also need the notes that I have left you for chapter 6 and 7. So all we are doing today is talking about probability. What is the chance of? There's a lot of different fancy ways to say it. You know me, I really don't get bogged down in the details. The biggest thing I want you to understand is we're talking about what's the chance of something going to happen. And most importantly, is something usual or unusual. So whenever we study probability, we always talk about what probability is. It is the chance of an event occurring. End of story. Now, it's important, though, that we get some terms down correctly that we'll be using going forward. We have independent events and dependent events. Independent events are events that occur without the influence of anything else. Dependent events, and we'll have lots of examples of this going forward, of both of these going forward. Dependent events are when one event is influenced by another. So we also have sampling with replacement and sampling without replacement. So what does that mean? So when we have, the easiest way to explain this is when we have a deck of cards, and I do have an example of this to show you. So when we sample with sample with replacement, let's say we have a deck of 10 cards. We pull one card and then we put it back in the deck. So that's sampling with replacement. We replace the deck, we replace each one. So if we have 10 cards, the probability of pulling one card out of the deck that we want is 1 of 10. What's the chance of pulling a card? 1 out of 10. If we put that card back in, the probabilities stay the same. We still have a 1 in 10 shot of pulling a card. When we sample without replacement, however, we pull a card and we leave that card out. Now there's only 9 cards left in the deck. That's sampling without replacement. We do not replace that card. When you sample without replacement, you change your odds going forward. And again, I have lots of examples like this. I like to get this kind of nitty-gritty stuff out of the way first. So basic probability, the probability of any event occurring is the number of outcomes that could be classified as whatever it is that you're measuring over the total number of outcomes. So let's go to my examples and I'll show you what I'm talking about. So when you are flipping a coin, and in statistics, you hear a lot about weighted coins and not weighted coins. If you are flipping a not weighted coin, you have a probability of flipping that coin and getting a heads or a tails. So the probability of getting heads, so that's what this means, probability of getting a heads is 1 over 2. You could also say it's 0.5, or that's 1 divided by 2 is 0.5, or you can say there's a 50% chance of getting a heads. Now, here's my example for sampling without replacement. Sampling with and without replacement, sorry. So in my first example here, you have a deck of cards, 4 suits. For those of you guys who don't know about decks of cards, because I know cards aren't played a lot anymore, cards have 52 cards, and a deck of cards has 52 cards in it, and there's 4 suits: hearts, diamonds, spades, and clubs. Your possibility of pulling a spade is 13 over 52, or 1 over 4. You can also say 0.25 or 25%. Those are great too. Great ways to say them too. So 4 suits, how did I get the 13? There's 4 suits. 4 divided by 12 is 13. 13 over 52, a 1 in 4 chance. You've pulled, so you're going to pull a card and then you're going to replace it. Your odds don't change from the first pull to the second pull. However, what happens, again, this is another example of sampling of the same idea, but now we are not going to we're not going to sample with replacement, we are going to sample without replacement. So you have a deck of cards. There's 4 suits: hearts, diamonds, spades, and clubs. The probability of pulling a heart out in this first draw is 13 over 52. You'll notice it's the same probability of pulling a spade. However, this time we're going to pull a spade and we're not going to replace the card. Now we want to know on our second pull, what is the probability of pulling that heart out? the probability here changes. It goes from 13 over 52 to 13 over 51. These are all possible outcomes still, but we've pulled out a spade already, and so the number of cards has diminished. So you'll see lots of examples of this in your book. And if you need other examples, or if we want to go over this when we meet again after your exam, that's great as well. I know that for many, this is a hard exam. This is hard stuff. Let's go over a very basic example and this we've seen before. There's 30 candies in a jar. There's 10 red, 7 blue, 8 green, and 5 orange. There's a total of 30 candies in the jar. So the way that we measure the probability of each is we just put the 10 red over the 30 equals 1/3. The 7 blue over 30, we don't really do anything with that. You could divide it out if you want to. With the green candies, there's 8 over 30, or a probability of 4 over 4/15. Or with the orange candy, there's a probability of 5 over 30, or 1 in 6 chance of getting an orange. Again, just probability. Here, we could then say, well, there's a lot more red than there are orange. There's more red than any other. So red is likely to occur, but then as you get further down to like the orange, unlikely to occur. Those words likely and unlikely, very important as we go forward. And again, these are the oldies but goodies. Probability of tails, 1 and 2 or 50%. Probability of pulling one card out of a deck, 13 over 52 or 1/4. So now we can say, okay, how does this relate to what we've been learning and what we're going to? Well, here it is. We can say the probability here of getting a score in one of the tails is unlikely. The probability of being out in the tails is only 0.13%. And you guys have seen these percentages for a couple lectures now. Need my water. The probability of being between 120 and a score of 130 is 2.15%. So we can start to play with these probabilities. And as we talked about last time with z-scores, the question is, what happens when we have a score in the middle that is not one of these whole number z-scores or the standard deviations? And we now talk about, yes, these are the standard deviations, but these are now also the z-scores. And we learned that the z-score formula is x minus x bar over the standard deviation of x. But again, what's your probability if you get a score in between? So let's go over that. We are going to be looking at our first set of tables. It's the z-score table. Now, point of note, I do not use the z-score table that's in your book. Why? Because I found an easier one. So you will see I have left you a copy of those tables. So a z-score table tells you that if you get a z-score that is not a whole number, you go into the z-score table, and don't worry, we're going to do this example in a couple different ways. You go into the z-score table and you can look to see what percentage is above and below the z-score. So while these are nice to know, now we're getting a little bit more into the details of it. So let's look at that example of a z-score of 0.163. So if this happens, we use this method, we use this process when the z-score does not equal a whole number. So if you have a z-score, like I said, that is positive 1.63, and you want to know what's the percent above and what's the percent below, you go back to this z-score table. It's did I use 1.63? Yeah, 1.63. You find that in the table. I took this little snippet for you. 1.63. And we look very carefully. And the reason why I like this is because the columns are all labeled for you. So it is the z-score, what's at that z-score in the tail beyond, and what's at 1.63. What is the column B is this part right here. So this is column C, and this is in column B. So you just match up those numbers. Now, moving a step ahead, which of course you know me, I keep going over the same concept so everyone gets it. You have C, you have B, and then this everything here is 50%. Now, you can, as you're learning, put column C here, put column B here, and then duplicate them. Below or above the mean is always 50%, so you don't have to do that. But I know many of you will want to, so that's fine too. So what do? We look in the chart and we learn that at a z-score of 1.63, there are 0.0516 or 5.16 above that z-score and 44.85 between the z-score and the mean. Remember, column B, column C. So we can say that 0.0516 is above, or 94.84 is below. Now, where the heck did I get the 94.84? I added the 3 columns left that are below. So you can add all of them, or as you get better at this, you will notice that this simply equals 50%. So let's do another example. Suppose you get a z-score of negative 0.34. You would go to the z-table on page 422 in that table. Now we're dealing with a z-score on the other side. Now remember, column B and column C, 50% is above. Between 0, this is column B, between 0 and the score, between the mean and the score, we have 0.1331, 13.31. And then from the mean, from our z-score to the end of the distribution, we have 0.3669. Make sure, and again, there's more examples in the book and you'll be doing some for homework, make sure that you are going into the z-table, you look for your z-score, and then the most confusing part is just lining up the columns with the percentages. So I'm going to leave you with that, finding a z-score, going into the table, and finding the percentages. And we will do more examples of this when we come back together as a class next week. Okay. Believe it or not, I mean, that's all that there is in chapter 6. It's very simple. I don't complicate it, make you do a lot of probabilities or, calculate a lot of things because it's really not important. Like I said, the most important thing that you understand is what likely and unlikely is, and then how to find the z-score in the table, okay, and the percentage above and below. So chapter 7 is all about, well, it's nice to think that we're always just going to draw one sample. The question is, what if there are hundreds of thousands of samples available to us? The location of any score in a sample can be represented with a z-score. So that's what we've been working on. You have one score in a sample that you've taken. You want to know that score's z-score. However, when you sample from a population, since there are so many options, we need another procedure for that z-score. So what we want to do is we want to obtain what is the probability of obtaining a certain sample with a certain mean attached to it. And I know that gets a little confusing, but what we do is here, I've drawn it out for you in one of my famous pictures. Let me see if I can make this a little smaller. So when you read in your book about the sampling distribution of the means, this is what they talk about. And this picture has helped a lot of students get through this concept. We have a population here, and we want to select a sample. Now we can select one sample, or there's actually, well, there's a finite number of samples, each with a population of a certain size. Sampling distribution of the means is theoretical. So, but what we do is we account for the fact that there's a certain number of samples of this size. We only pull one. However, the theory is that if you pulled all of them and did your descriptive statistics and got a mean on all of them, you would get this thing, the sampling distribution of the means. You would have a mean for every sample, and those means would form a distribution. Okay, so I'll say it one more time because I know it's really confusing when you first hear it. You have a population, you're going to pull a sample, but there are other samples that you could pull. If you pulled all of them, this would take an enormous amount of time and effort and money, you would get a mean for each sample. And each mean would be plotted on the histogram and would form the sampling distribution of the means. That's what it's known as. So this is where we now spend in this sampling distribution of the means and understanding it. Now your book, the good news for you guys is that your book describes it in another way. So for those of you who need to hear and then read and then do problems, this method works out perfectly. You've heard it from me. And then it's almost like degrees of freedom. Like it's kind of confusing when you first hear it. As long as you're reading and listening and doing, it'll start to sink in. The most important part is that you realize when you are pulling a sample and trying to figure out if it is likely or unlikely, you use ready for it? You use the standard deviation of the sampling distribution of the means. I know, it's a lot. So we had all these little sample means are going to form a distribution. This distribution in itself is going to have a standard deviation, and that is what we call standard error. So first, what we need to do is compute. Where did my standard error formula go? Oh no. Okay, I'll have to put that in for you. So the first thing you do is you compute the standard error. Is it behind here? No, this is unfortunate. I probably have it on another slide. Hold on. So when we have a z-score of a sample and we want to determine, is it likely or unlikely? And lots of means went into it. We're going to use the standard error. So again, random sampling is when we pull that sample from a population and every person has an equal chance of getting in. We've selected a sample size, and based on that sample size, that's how the sampling distribution of the means is created. Again, in theory. We want our samples to be representative. They're not always representative, though. Sometimes flunky things can happen. So we have to account for that as well. Now, we went over what a representative sample is. And a representative sample simply says that all of the characteristics in the population have an equal chance of getting into your study. Sorry, you can hear my dog barking. He always thinks someone's attacking the house. And we went over this a lot. So we have a population, we're going to sample, this is random selection, and then we're going to assign random assignment. So we're dealing right here in this process. And then we're going to look at, is the sample that we pulled representative of the population? So now we're going to have to determine that. Now the central limit theory, so we don't know. When you pull a sample, you actually never know whether it's representative or not. We assume it is. And the central limit theorem is what allows us to do this. So the central limit theorem claims that for a normal distribution, we've got it. It's okay. So a normal distribution over 30 subjects, there's going to be a mu, and the underlying mu, remember, is the population mean. And there's a standard deviation that we can calculate for that mean. Now, like I said, what all of 1 through 3 means is once you've got it, like it's good. Once you've got more than 30 people and you can take all possible samples, your mean and your standard deviation are on point. So when we go back and pull our sample, as long as it's more than 30 people, the central limit theorem says you're good. Now, I've already discussed that and explained the sampling distribution of the means. So basically, again, all possible samples are taken, put on the distribution, and the distribution will always be normal. That's what we can assume. And then what we can do is we can take the probabilities of those z-scores. Oh, there's standard error. I know I had it somewhere. Okay, so the standard deviation of the sampling distribution of the means is the standard error of the mean. Standard deviation of the sampling distribution of the means is called the standard error of the mean. It is a lot of words, and all it means is that if you have sampled and you are now going to take a z-score and the standard error, if you're going to compute a z-score, you have to use a standard error. So the formula for standard error is you take the standard deviation that you computed in your sample, but now you take a correction. You just take your standard, like just the same way that we calculated in class, and now you have to divide it by something. So you divide it by the square root of n. This turns the standard error, this turns your standard deviation into an unbiased statistic. And again, what does that mean? That just means that we've got it. So again, when we have a z-score and we've taken it from a sample, the z now is x bar minus mu over standard error. And the standard error is the standard deviation over the square root of n. And then we can use the z-table to find out where this is in the population or in the population's distribution. Now, what we're trying to do here is compare distributions. This is what it allows us to do. We can then take scores and samples from bigger distributions, and we will have more examples of those going forward. This just gives you an example, though, of what it's like to compare those two distributions. You can compare English to statistics. Sorry, I just need a drink of water. And we'll be going over this in greater detail. So what I did here was I left us an example, and I'm going to walk through it quickly, like I always do. So, and I will put this example also onto our spreadsheet so you have it written out another way. So this is the same old data set that we've been using. There's these 18 scores. So the first thing that we can do is we can get a z-score for each of these scores, right? And I'll do that I'm going to do that for you in the document and in the spreadsheet, so you can see how I got a z-score for each one, and then you can get the z-score percent above and below. So as an example, I just left one here. We know from doing this problem a lot, the mean is 13.67 of the, so if we know that the mean is 13.67 and the standard deviation is 1.56, our z-score of any one particular score is going to be the 13 minus 13.67 over 1.56, and that is going to be a z-score of 0.43. However, now if we have a sample mean of 13 and we have 18 scores and we know that our mean is 12 and we have 2.58, we've taken a sample. So these scores are just not any random set of scores. This is now when we would use the standard error. So up here when we did it, this is just using information that we have about the population. Now we've sampled. So if X bar equals, again, I just read all those. So we have to use the formula for standard error. So here's how you compute the standard error. And I'm going to write, I have all this written out for you as well. And then you're going to find the standard error. It's going to be 2.5 over the square root of 18.58. And you wind up with 0.589. And now you use that in your Z statistic. So you find the Z score 13 minus 12 over 0.589 equals 1.70. So I know that was a lot, and I know I jump around and it's a little confusing because it's the first time you're hearing it. I'm going to go back in as I've gone through this for as many times as I've taught this. I'm going to go back in and write this all out for you so you have that in my notes. I will also include it on the spreadsheet so you can see the numbers of it. Sometimes that is helpful. And then do your homework for 6 and 7. It's a lot more easier than it seems here. And let me know if you have any questions. Okay, that's it for now. Thanks so much. Bye-bye.